Okay, so today we're going to talk about the linear regression assignment. A Chinese automobile company aspires to enter the US market by setting up their manufacturing unit there and producing cars locally to give competition to their US and European counterparts. They want to understand the factors affecting the pricing of cars in the American market, since those may be very different from the Chinese market. Essentially, the company wants to know which variables are significant in predicting the price of a car, how well those variables describe the price of the car. So based on various market surveys, the consulting firm has gathered a large data set of different types of cars across the American market. So the goal of this assignment is to model the price of cars with the available independent variables. It will be used by the management to understand how exactly the prices vary with the independent variables. They can accordingly manipulate the design of the cars, the business strategy, etc. to meet certain price levels. Further, the model will be a good way for the management to understand the pricing dynamics of a new market. We've used multiple linear regression to model this solution as it explains the relationship between the dependent variable, which is the price, and the various independent variables in this case. Linear regression is typically used to understand which among the independent variables are related to the dependent variable and to explore the forms of these relationships. When the dependent or the target variable is not continuous, unbounded, and measured on an interval or ratio scale, the model will not meet the assumptions of the general linear model, and hence we cannot use linear regression. For example, although ordinal variables like numbers, the distance between their values isn't equal in a true numerical sense, so it doesn't make sense to apply numerical operations like addition and division to them. So to choose the relevant features, we build a model containing all the variables. Then we check the variation inflation factor and summary, remove variables with high VIF, typically greater than 2, and which are insignificant, where P is greater than 0.05, one by one. If the model has variables which have a high VIF and are significant, check and remove other variables. After removing the insignificant variables, the VIFs should decline. If some variables still have a high VIF, remove the variable which is relatively less significant. Now the variables will be significant. So if the number of variables is still high, we have to remove them in order of insignificance until we arrive at a limited number of variables that explain the model well. Now stepwise selection is a combination of forward and backward selection. We may start with all variables as in a backward selection or start with a single variable as in forward selection. Forward selection is rarely used in the industry. On the other hand, backward and stepwise selection are most commonly used. Multicollinearity. It may be that some variables could have some relation amongst themselves. The variables may be highly collinear to each other that could make one or more variables insignificant in the multivariable model. Multicollinearity makes it difficult to assess the individual impact of a predictor. The model building process. So typically we build a model containing all the variables, check the VIF and summary, remove the variables with high VIF and insignificance. A very important parameter of this analysis is the p-value. In regression model building, the null hypothesis corresponding to each p-value is that the corresponding independent variable does not impact the dependent variable. So the p-value indicates the probability that the null hypothesis is true. Therefore, a low p-value, which is less than 0.05, indicates that we can reject the null hypothesis. The higher the VIF, the higher the multicollinearity. But variables with a high VIF may be statistically significant, in which case we'll have to first check for other insignificant variables before removing the variables with a higher VIF and lower p-values. Typically, we take VIF equal to 2 as the threshold, but it will depend on the business case. Evaluation of the model, there are a few parameters. R squared, which is the square of the correlation between variables, it is related to correlation. So if R equals -1, it's a perfect negative correlation. If it's 1, then it's perfect positive correlation. And if it's 0, then there is no linear relationship between the variables. So the R squared between the predicted value and the actual value in the test set should be high. In general, it is desired that the R square on the test data be high and as similar to the R squared on the training set as possible. So R square always increases when the number of variables increases. Adjusted R square imposes a penalty if the increase in R square is small, hence it is a better metric to assess how well the model fits the data. Adjusted R square decreases when added variable has negligible correlation with the outcome. The strength of a linear regression model is defined as 1 minus RSS by TSS, where RSS or the residual sum of squares and TSS is the total sum of squares. As a model becomes more complex, it uses the training data more and there is a decrease in bias, but an increase in variance. If a model has many parameters, which means generally low bias, it will fit the data well, but yield high variance. Conversely, if the model has few parameters, generally high bias, it may not fit the data particularly well, but this will not change much as for different data sets, which is low variance. Low variance algorithms tend to be less complex with simple or rigid underlying structure. They train the models that are consistent but inaccurate on an average. These include linear or parametric algorithms. On the other hand, low bias or high variance algorithms tend to be more complex with flexible underlying structure. They train models that are accurate on average but inconsistent. These include non-linear and non-parametric algorithms such as decision trees. So this trade-off in complexity is why there's a trade-off in bias and variance. An algorithm cannot simultaneously be more complex and less complex. Linear regression models has 5 key assumptions: linear relationship, multivariate normality, no or little multicollinearity, no autocorrelation, and homoscedasticity. Why should errors be normally distributed? The error term can be thought of as the composite of a number of minor influences or errors. So as the number of these minor influences get larger, the distribution of the errors tend to approach the normal distribution. If the random errors are in the process are not normally distributed, then any inferences we've made about the process may be incorrect. So if we are using regression analysis to generate predictions, there is a caveat. Prediction intervals are calculated based on the assumption that the residuals are normally distributed. So if the residuals are not normal, then the prediction intervals may be inaccurate. Finally, the scatter plot is a good way to check whether the data is homoscedastic, which means that the residuals are equal across the regression line. Thank you.